All right, this is a review on proportions. Here I have a list of things that I'd like you to know about proportions. Does it seem a little bit small? I want you to think before I do it how I, here on my iPad, would have to touch that to grow it out to where you can see it. You might think about pinching and then moving your fingers diagonally, or you might think about grabbing it by the corner and dragging it diagonally. And what we're doing there is we're growing and shrinking this thing proportionally. So you guys have an understanding of proportional growth and shrinking already. And so these are then the 8 things that I want you to know about proportions, and then a couple things about that last one. All right, I'm going to go through these real quickly. Number 1, order matters. Oh my goodness, order matters. If I say cats to dogs, the ratio needs to be cats, then dogs. And that goes down with number 7. So I'm going to skip down to number 7. Number 1 goes with number 7. When you're setting up these things out of some sort of a story problem or some sort of an actual real world problem, make sure you use your labels. Don't just put naked numbers out there inside of a proportion. Put the labels there to make sure you're getting them in the right spots. Number 2, their cross products are equal. This is what we use for a shortcut for how to solve them. When I say cross products are equal, I'm talking about, let's say I have 3/8, and hopefully you know that that is equal to 6/16, right? How do I know that? Well, because I doubled the top and I doubled the bottom. And if I double both the top and the bottom, I have the exact same ratio, just at different size pieces. Okay? So if that's true and these are equal, then one thing that we will notice is that if you take the cross products, products is the answer to a multiplication problem, 6 times 8 is 48. And guess what? 16 times 3 is also 48. And you can use this with anyone. We'll just do one more quick one that you know pretty easily. 1/2 is 5/10, right? Well, 2 times 5 is 10, and 1 times 10 is 10. The cross products are always equal in a proportion. Number 3 says they are read A is to B as C is to D, and that goes down with number 6 as well. So number 3 and 6 kind of fit together. This is read A has a relationship with B, and it has the exact same relationship with B that C does to D. So A is to B as C is to D. And this might sound familiar if I said something like hat is to head as shoe is to, and you would be looking for what relationship. Well, isn't hat the clothing that goes on the head, body part? Well, then shoe is the clothing that goes on the body part of foot. So you know that hat is to head as shoe is to foot. And you notice these two have a relationship up here because they have the same label. The label for those would be clothing. These two have the same label, which is body part. And so now you can see that we have some relationships there, and that's why number 6 says there's special connections. The A and the B are connected because they're in the same ratio. The C and the D are connected because they're in the same ratio. So they're related up and down. And then A and C are related because they have the same label, or they're the same part, okay, of that ratio. And then B and D have a relationship. The only two that are not connected are those A and that D, and that B and that C. Those we use with cross products, but they actually have nothing to do with each other. Think about it down here. Does shoe have anything to do with head? Nothing to do with it, right? Shoe is a clothing article of clothing, and head is a body part. They have nothing to do with each other. Okay? Number 4 is just a definition. It's a ratio equal to a ratio. So when I wrote 1/2 equals 5/10, this is a ratio, which is just a comparison of two numbers. This is a ratio, comparison of two numbers, and we are saying they are equal. So it's a ratio equal to a ratio. Number 5 is just a warning that I've learned after teaching for a number of years. Kids look at it and they try to cross-simplify it as if it's a multiplication of fractions problem. This is not a multiplication of fractions problem. So it's a proportion. They're equal. We can't cross-simplify them. Number 8, finally, is have a constant ratio. That means that when I divide them, if I go back to that example of 1/2, 1/2 equals 5/10. If I divide them, and we're going to get used to dividing these as y divided by x, or output divided by input. But if I divided those right now, this would turn out to be 0.5 and this would turn out to be 0.5. Or if you simplified them, they'd be 1/2 and 1/2. Either way, if you simplify them down to a constant ratio or a unit rate, they're going to match. And now, when we get down to that constant ratio is the unit rate. It's also called the constant rate of change. Now, anything that's linear will have a constant rate of change. So if you graph a line, it will have a constant rate of change. But this one not only has a constant rate of change, it has a constant ratio, meaning if you simply divide them, you'll get the same number every time. This thing is also called the constant of proportionality. When you graph it as a line, it's the slope of the line. It's the coefficient of x in y equals mx. So it's the m portion of that. And you can find it every time by taking y divided by x. Y divided by x, if it's proportional, you'll get the same thing each time. All right, so here's just a little bit of practice. I have set up this whole arrangement of basically equivalent fractions, if you think about it that way. And I want to remind you that the cross products are equal. So 1 times 4 is 4, and 2 times 2 is 4. 2 times 6 is 12, and 3 times 4 is 12. 3 times 8 is 24, 4 times 6 is 24. 4 times 10 is 40, and 5 times 8 is 40. 10 times 6 is 60, and 5 times 12 is 60. And the next one, we have a missing spot. So one thing you can look to do is see if there's a way that you got there directly. Like, what did I do to 6 to get to 9? And maybe you can't recognize that. So you could go back to one that matches nicely with 9, like 3. Didn't you take 3 times 3 to get to 9? So you could do that to get this number, right? 6 times 3, of course, is 18. So we know that's going to be 18. But I want to show you a different way, and that's called using that idea of cross products to solve it. What you know is if this is an m or some sort of variable that we don't know, you know that 12 times 9, which is 108, is equal to 6 times m. And so you might notice what you did is you multiplied the two diagonals, the two that were diagonal, 9 and 12, and got a 108. And now you have this problem, which is an algebraic equation, and you know to undo times 6, you have to divide by 6. So let me write down the problem you actually did. You did 9 times 12 divided by 6. That's multiply the diagonals, 9 times 12, and then divide by the other one. So multiply the two diagonals, divide by the other one, and you get your answer, which was, of course, 18. Now we can do that exact same thing here with the next problem. So we can take 9 times 52, which is 468, and then we can divide it by the other one, because remember, 18 times m is going to equal that, 468, so I'm just going to divide by 18 to solve. And you get an answer of 26, so m must be 26. Now I just want to point you to the picture of this. What is shaded right now is 1/2, that's our first ratio. Could I have cut it differently and made it 2 out of 4 pieces? Same ratio, did not change the amount of green, right, or the amount of white, I just changed how it was cut. Couldn't I have cut it into 3/6? Haven't changed the amount of green or white, once again, I just changed the way it's cut, but we still have a constant ratio. I'll do one more. If I cut it into 8ths, you can see, once again, I did not change the amount of green or white. I just changed how it was cut, and now it's 4 out of 8. Once again, all of those have a constant ratio, the constant ratio being 1/2. If you simplified them all, if you took away all those lines in between that I did, you're back down to the constant ratio of 1/2. Now I want to do an actual story problem with it. If 5 sodas cost $5.80, how much will 3 cost? Well, I know how most of you would attack this problem. You would say, well, let's find a unit rate. So we're basically going to take $5.80 and divide it by 5 to find out what it costs for 1 soda. When I do that, I get $1.16, and we write that as $1.16 per soda. That way we have both labels, and that makes it a unit rate. Okay? But we want to know how many 3 cost, so wouldn't you just multiply by 3? So I want you to think about what we did. we divided by 5 and we multiplied by 3. If I multiply by 3 on that, I'm going to get $3.48 is what it's going to cost me for 3 of those sodas. Another way to do that is to have it set up like this. Use your same label. So this is going to be dollars, this is going to be sodas. So I have this many $5.80 for 5 sodas, and I want to know how many dollars for 3 sodas, so that the 3 goes on the bottom. And now another way you could do this is multiply the diagonals and divide by 5. I want you to think about it. The first way, we would divide by 5 and multiply by 3. On the second way, we multiplied by 3 and divided by 5. Isn't that the exact same math? Now, we did it in a different order, but remember, you can change the order if you think about it as division as multiply by the reciprocal. Then you can have the commutative property. So I wanted to show you have a way of solving this where you actually do a proportion without writing a proportion. With that idea in mind, I want to bring up a double number line because I think it's a really good way to think about proportions. So I checked my gas mileage. I took a 336 mile trip and it took me 12 gallons. So I have that ratio of 336 miles to 12 gallons. And one thing that people want to do is automatically go down to how much it is for 1. And that makes sense because unit rates make sense. So if I want to shrink this down to 1 gallon, one way is just to take the 2 that I know and then divide them. So if I take 336 divided by 12, then I will get 28. So it would take 28 miles for 1 gallon. That is a unit rate. But we could do some other things, like if I cut the gallons in half to 6, if it was 6 gallons, wouldn't I have to cut the miles in half to be 168? I could cut that 6 gallons in half and get down to 3 gallons by dividing that 168 miles by 2, and that would get me to 84 miles. So we can do this, and we have kind of an understanding of halving, or we could take things in thirds if they come out even. So at like 12, I could have divided it by 4 to get to 3. I could divide by 3 to get to 12. But what if it's something that doesn't go in nicely with 12? Like maybe I wanted 7 gallons. Well, one way to do that is shrink it down to a unit rate, and this is why we use unit rates, because 1 is friendly with every other number. So if I divided by 12, I would get down to 1 gallon, and then I could multiply by 7 to grow it back up to 7 gallons. Does that make sense? That's one way of thinking about it, is shrink it down to 1 proportionally, and then grow it back out to whatever number you want, because 1 goes with every number. How else could you have done it? You could have set it up like this, and I like to label mine in the middle most of the time. That way it works for both sides. So the one that I know is 336 miles and 12 gallons. The one that I want to know is 7 gallons. And all of a sudden I'm ready to grab my calculator, multiply the diagonals, and divide by the other one. And it works for other things. Like say I wanted to take a trip that was 525 miles. Well, 525 miles and 336 miles don't play nicely together. So what could we do? We could shrink it down to 1 mile, how much gas, and then grow it back up to 525 miles. Now notice, that's a different unit rate than what we did. We did miles per gallon, and now I'm talking about gallons per mile. That's because I want to solve for miles. That confuses some people, but one way to fix it is just go to a proportion instead. Miles, gallons. The one that I already know is 336 miles for 12 gallons, and now I want 525 miles. All I'm ready to do is multiply the diagonals and divide by the other one. And that gets me my answer of 18.75, and it's already got the label down there with it. It would take me 18.75 gallons to take this trip. This number line, I think, is a good way of thinking about it because it helps you understand that you can shrink things or grow things proportionally along it to find things that play nicely with 12 gallons and play nicely with 336 miles, or something as ugly as 525 and 336. We go straight to our proportion and we can solve it. And one last little bit of review, and that's how we know something is proportional, or how we can kind of tell it's proportional. So the first one's graphed. I have a number of graphs there, only 2 of which are proportional. Can you tell which ones are proportional? It's the purple one and the gray one, right? And I'll prove that to you. I'm going to look at maybe the green one. So I look at the green one and I have the points 1, 6 that I have right there. and I have the point 39. And one thing you'll notice is they're all in a straight line. What that means is they all have a constant rate of change. They're all going, have the same rise over run. But when I divide this one, and I always want to divide in the order of y divided by x, I take 6 divided by 1, I get 6. I take 9 divided by 3, I get 3. These do not match. We do not have a constant ratio. We have a constant rate of change, but when I simply divide the y by the x, I don't have something that matches. Now compare that to the gray line. The gray line, I have the points 5, 1, that would be that point right there, and 10, 2. Now, people will make a mistake on this one a lot of times, and they'll tell me that the constant rate of change is 5, or that the slope is 5, because they like to take the big number divided by the little number. That is not the case. We do not take the big number divided by the little number. We take the y divided by the x. So, remember, all points come in the order y, or xy, excuse me, said that backwards. So I'm going to be taking 1 and dividing it by 5, and I get 0.2 when I do that, if I do it on a calculator. And then I'm going to take 2, and I'm going to divide it by 10, and guess what I get? 0.2. Another way of thinking about that is this 2/10 simplifies to 1/5. So as a fraction, our constant rate of change is 1/5. As a decimal, it's 0.2. And you might notice those match, right? So that's a constant ratio as well as a constant rate of change. So it's going up the same amount each time. The slope is the same, but also when I divide them, I get the exact same thing. Now, the reason is because they hit this point here. They hit 0, 0. That's one key issue with proportions is all these others are going to be in this form, y equals mx plus b, where m is the slope and b is where it hits the y-axis. So this yellow line, for example, hits the axis at positive 6, right? So this number on that one would be a 6. The number on the two proportional lines, the gray one and the purple one, is 0, and that means it disappears because anything plus 0 is itself. Does that make sense? So if I were to write the one that we did, this gray line, I know the slope is 1/5, so I could write it as y equals 1/5 x, and there is no boyfriend, or that's what I always call it, is the boyfriend, your mama's ex-boyfriend, but there is no y-intercept because it's an understood plus 0 because it hits the origin. So let's check the table. How do I check to see if it's proportional? I take y divided by x. So I take 15 divided by 3 and I get 5. And I take 20 and I divide it by 4 and I get 5. And I take 32 and divide it by 8 and I get 4. And I take 33 and I divide it by 11 and I get 3. So now when you're looking at it, you think, oh, looked like it was going to be proportional. If I would have stopped the graph right here, these two would have been proportional, but then it changed. So what you had is it was going at a constant rate of change for a while, and then it changed slope. Does that make sense? It changed slope a couple times, so it's not linear, so that makes it not proportional. Try the last one also. So I would take 8 divided by 4. 8 divided by 4 is 2. 11 divided by 5 is 2.2, and already I don't need to check anymore because I can already tell you it's not proportional because of that. Now I'm going to go ahead and take a second and go ahead and show you the rest of that just so we know, so we can write that linear equation. If it's not proportional, you might try this. Difference of y means you're going to subtract the y's over difference of x. Now you need to keep them in the same order. So I'm going to be doing 11 minus 8, which is 3, and 5 minus 4, which is 1. And I then divide them and I get 3. Let me try that again. I do 17 minus 11, which is 6. I do 7 minus 5, which is 2, and I get 3. So now they match, but notice I had to do subtraction, which means it's not a constant ratio because I had some sort of an adjustment there. So I can start writing that equation, y equals 3x, there's your slope, right? Because it does have a constant rate of change. But something else happened back here. Because if it were just times 3, then when I took 4 times 3, I would have been at 12. But I didn't end up at 12, I ended up at 8. So what adjustment had to be there? From 12 to 8, I had to subtract 4. And that's how you write the linear equation, even if it's not proportional. So let me try that again. If I would have taken 5 times 3, I would have got 15. But since I have a minus 4, that's why I started at 11 instead of 15. And if you wanted to graph that, just so you understand, it would be hitting the y-axis at -4, so it's going right down here. And then this is the slope, the constant rate of change, so it would be going up 1, 2, 3, right 1, up 1, 2, 3, right 1. Not doing a very good job of graphing that. So that's what that line would actually look like. Notice it does not hit the origin. That's why it's not proportional. We'll never have a constant ratio.